The ground beneath the Pacific Ocean is moving right now. Not metaphorically, not slowly in geological time beyond human perception, but measurably, continuously, at rates instruments can track. And where that movement is greatest, where one vast slab of rock is being forced beneath another, the seafloor opens into a trench. Those trenches are not passive scars. They are the surface expression of a process that builds pressure across hundreds of kilometers of locked rock, pressure that eventually, inevitably, releases. The question is not whether that release will come. The question is what it will look like when it does. Oceanic trenches form at convergent plate boundaries, places where two lithospheric plates move toward each other. When oceanic crust meets another plate, it subducts, it bends downward and descends into the mantle beneath. The trench is the crease where that bending begins, a V-shaped valley cut into the seafloor, typically 50 to 100 kilometers wide and 3 to 4 kilometers deeper than the surrounding ocean floor. Thousands of kilometers long, the world contains roughly 50,000 kilometers of these convergent margins concentrated around the Pacific, but also extending into the eastern Indian Ocean and beyond. The largest trenches reach depths that compress the mind. The Challenger Deep in the Mariana Trench descends to 10,994 meters below sea level. That is nearly 11 kilometers of water pressing down, a column of ocean that generates pressures no surface instrument was ever designed to survive intact. At those depths, temperature approaches freezing. Pressure reaches more than 1,000 times what a person experiences standing at sea level. The rock itself behaves differently under such conditions. The subducting slab carries sediment with it as it descends, and those sediments are saturated with fluid. As the slab is forced deeper, that fluid is squeezed out, returning to the surface along the trench floor. The result is a set of formations called mud volcanoes and cold seeps, places where methane and sulfur-rich water push upward through the seafloor and sustain ecosystems built not on sunlight, but on chemical energy. Chemotrophic microorganisms form the base of these communities, supporting life in conditions that would be lethal to almost every surface organism. These are not fringe environments. They are ecosystems tied directly to the mechanical process of subduction, fed by the very fluids that the grinding plates wring from the rock, and those fluids matter beyond biology. Fluid pressure at the plate interface affects whether locked sections of crust slip gradually or lock and store energy. The difference between those two behaviors is the difference between a quiet margin and a megathrust. The tectonic plates moving into these trenches do not do so smoothly. They move at rates ranging from a few millimeters to more than 10 centimeters per year. And globally, the oceanic lithosphere descends into trenches at a rate of roughly 3 square kilometers per year. That motion is not frictionless. Where the descending slab and the overriding plate are coupled, where friction holds them together, strain accumulates. The interface does not slip. Instead, it locks, and the plates on either side deform around it, bending and compressing over years, decades, centuries. When that lock finally breaks, the energy stored across the entire coupled zone releases at once. This is a megathrust earthquake. The scale is not comparable to ordinary seismic events. The largest earthquakes ever recorded, including the 1960 Valdivia earthquake and the 2004 Indian Ocean earthquake, occurred at subduction zones, at convergent margins, at precisely the kind of boundary that trenches mark. Detecting and measuring the state of that interface is where science runs into its hardest limits. Instruments on the ocean surface can track plate motion. GPS networks on nearby land can measure the slow deformation of the crust as strain builds. But the interface itself, the locked zone kilometers beneath the seafloor, cannot be directly observed. seismic reflection surveys can image the structure of the crust down to certain depths, but the resolution at the depths where locking occurs is constrained by the wavelength of the acoustic signal and the complexity of the rock above. Drilling programs have penetrated the upper portions of subduction zones in a small number of locations, recovering core samples and placing instruments in boreholes. Those instruments measure temperature, pressure, and seismic activity directly at depth. But each borehole is a single point in a system that spans hundreds of kilometers, and the cost and difficulty of deep ocean drilling means those data points remain sparse. The Cascadia subduction zone, off the Pacific coast of North America, presents a specific version of this problem. Its trench structure is completely buried under sediment, leaving no clear bathymetric expression on the seafloor. The fundamental plate tectonic structure is still an oceanic trench by definition, and the subduction is ongoing, but the surface signal that would otherwise alert observation is hidden. What lies beneath the sediment fill is inferred from seismic surveys, GPS deformation data, and the geological record of past events preserved in coastal marshes and offshore sediment cores. That record shows repeated great earthquakes separated by intervals of centuries. The last one occurred in January 1700, identified through a precise convergence of Japanese tsunami records, native oral history, and the dating of drowned coastal forests. The next one has not arrived. The most defensible explanation for why trenches represent exceptional earthquake hazard is mechanical and well-established. Subduction zones host the largest earthquakes because the coupled interface is vast. A strike-slip fault, where plates slide laterally past each other, can rupture a length measured in hundreds of kilometers. A subduction zone can rupture a length measured in thousands, and the rupture area extends downward as well, deeper into the earth. More area means more stored strain. More stored strain means more energy in the release. The trench itself is the surface indicator of where that coupling zone begins. It marks the point where the subducting plate bends away from the surface, where the geometry transitions from horizontal to descending. The locked zone lies up-dip from that bend, between the trench and the coastline, generally at depths between roughly 5 and 50 kilometers beneath the seafloor. That zone is where the hazard is concentrated. What remains unresolved is not whether these zones can generate great earthquakes. That is established. What remains unresolved is the precise state of locking on any given section of any given subduction zone at any given moment. Sections of a subduction zone can be fully locked, partially coupled, or creeping freely. The distribution of those states along the fault controls where rupture initiates, how far it propagates, and how much energy it ultimately releases. Determining that distribution requires data from the seafloor itself, and the seafloor is vast, deep, cold, and expensive to reach. Ocean bottom seismometers can be deployed and recovered to fill some of the gap between land networks and the trench. Geodetic measurements from seafloor benchmarks can track displacement. But the coverage is not continuous. The instruments have finite lifespans in a corrosive high-pressure environment, and the data must be interpreted through models that carry their own assumptions. A locked zone can appear quiet for decades before it ruptures. Quiet is not the same as safe. The precise, unresolved question at the center of this problem is this: at which subduction zones is the locked interface currently storing enough strain across a wide enough area to produce a rupture comparable to the largest events in the geological record? And how close is any of those zones to failure? That question cannot be answered with current instrument coverage. It may not be answerable at all in the time frame that matters for the populations living above those zones. What can be said, with confidence grounded in measurement and physics, is that the trenches marking subduction zones are not passive features. They are the visible edge of a process that operates on timescales longer than recorded human history, but produces consequences that arrive in minutes. The sediment fills the trench, the fluid escapes upward and sustains ecosystems in the dark. The plates continue to converge. The strain continues to accumulate. And somewhere along those 50,000 kilometers of convergent margin, a section of locked rock is closer to its limit today than it was a century ago. The ocean does not announce what it is doing at depth. The instruments we have placed in it are sparse and imperfect, and the rock beneath the seafloor is beyond our direct reach across most of its extent. That is not a failure of science. It is the scale of the problem. An 11-kilometer deep trench extending for thousands of kilometers across the floor of the Pacific is not a place designed for human measurement. It is a place where the planet processes itself, where crust is recycled into the mantle, where the accumulated weight of geological time becomes, in the span of a few minutes, a wave. The trench exists whether we observe it or not. The process continues whether we understand it fully or not. What we have learned, with seismometers and drill cores and GPS arrays and ocean bottom pressure gauges, is enough to know the mechanism and to take the hazard seriously. What we have not learned, what the instruments at the edge of their range and the depth at the edge of reachability have not yet told us, is when. If the adjacent question troubles you, not only when a known zone might rupture, but whether there are buried subduction zones, sediment-filled and bathymetrically invisible, that have not yet been identified at all, the Cascadia example suggests that answer is not yet settled either.